still there is this tradition of 7 minutes later.
No, I mean, I don't think that was ever here at this place, but now just Harvard in general has abolished 7 minutes later, so
Okay.
go for it.
Okay, maybe first I can. Well, the lecture of today is independent from the first one, but the first lecture I told about something about Hodge locus. So something in one of the corollaries was missing. Some analytic varieties union of irreducible components of this bigger algebraic calculus. And some operator that might have two irreducible. Globally, it might be irreducible, but locally it is. It has many irreducible components, and when you go into global Hodge locus, you return back to the same place. You have different components. So this was the correction of this union of components. Okay, so let's go to the. Well, at this to justify today's lecture with whatever I told you in the first lecture. So the Hodge locus lives in some parameter space, and there are a lot of questions, conjectures, and so on. And the idea is that to pick up just one variety and try to understand the Hodge locus starting from this variety. And in the parameter space of the hypersurfaces, the most, I don't know, my favorite variety or the most well-known variety is the Fermat. So this projectilization of this guy, if you write the correct term, this guy is given. So we are dealing with the Fermat variety of degree d and dimension n. So today I will just talk about this variety, but as I said, the main idea is that starting from this one, I want to perturb this one into arbitrary hypersurface. I want to get some information about this Hodge loci, just looking at this variety. And okay. Mainly, as I said in my first lecture, the main difficulty of the Hodge conjecture is that we don't know how to construct algebraic cycles. And the construction of algebraic cycle, I think even we don't have produced 2% of the knowledge of constructing algebraic cycles. So it's a very difficult job. But the good point is that this guy has a lot of algebraic cycles. And once you have enough algebraic cycle to verify this, whatever called Hodge conjecture, even it's not so easy to verify the Hodge conjecture. And today we are going to see this in this case. Maybe first I start from one of the sample examples that we know, and actually the algorithm that I will write. It will produce the proof of this theorem in many examples. So maybe if I put names, I think there are all the names also. Main responsible 79. I will keep Yoda 3. So let's put the theorem. Okay, so B equal D prime or B prime or B equal to 4 or B co-prime with n plus 1 factorial. So if you have in this range of dimensions and degree, then if for let's say they call it Hodge lattice. Actually, this lattice I will define in the way that I like it with integrals, but if you are familiar with. So, Okay, so since I'm dealing with the Hodge conjecture, we're going to put in the middle homology, so this n will be just always an even number. I will use this n2, and I will not produce notation equal to k. But anyway, if you take the middle piece of the corresponding Dirac homology, intersect it with h and x q. Later I will be back to get to definition if you don't know. Then is generated by homology class of, let's say, linear algebraic. I will explain the ingredients of it. So, well, this is in some sense the verification of the Hodge conjecture, just in these cases. So let's a little bit explain the data. So I start from these linear algebraic cycles. So because of this nice monomial that you see, this guy has a lot of interesting cycles. Let's call them linear. And these are just linear spaces inside this guy, inside the Fermat. X0, for example, zeta 1, x1 equal to 0. So if you take roots of -1, you take a bunch of roots of -1, and then x3 equal to 0 by 1, x minus index is 1, x equal to 0. So how you can produce cycles here, you just this pair of x0d, x1d, factorize it, and then you will get this coefficient d root of -1, and this is inside xdn. Just as I said, for example, we write just x0 minus x, just this high school factorization. And after, so there are a lot of freedom to choose these cycles. For example, I can pair x0 with other variables, and also I can use different roots of -1. So in total one has, and one can index all these linear cycles. But in total, you will see that there is this number of, let's say, linear cycles inside. So this is the number of this kind of objects inside the Fermat. Or if you want to just take the automorphism of the XDN, you can make a permutation, you can multiply with the roots of unity, and so on. So in total, you have this number of linear cycles inside, and this number, at least in the case of, let's say, ND equal to 2 cubic surfaces famous. This is just the number 27. This is the famous 27 line in a cubic. And I think, well, in the case of also in the case of ND 2 4, this is 48, and which is corresponding to the K3 surface case. So they are these generalizations of this classical object. Okay, so whatever this part means, at the end, the theorem says that this guy is generated by the cohomology class that you associate to this these cycles. And maybe before going, so the main topic of this today is to replace Q with Z, and we will see if really the integral Hodge conjecture is true or not. But before going to this topic, maybe I tell some what is also known. So if you go beyond this range, beyond, let's say, this range of, let's say, A, then there is an article of, there is another class. Cycles. Well, it is introduced by Aoki Shioda, so I call them Aoki Shioda. It is originally introduced in this one of earlier articles of Shioda, but Aoki and Shioda then they verified the Hodge conjecture using this one. But at the end of the day, you can add at most p power of the prime and d, let's say twice. So you can go a little bit further in verification of Hodge conjecture. Just you can add these powers of primes and 2 powers of primes, p. And maybe to say that the difficulty, for example, this. So you see that in the theorem, for example, which numbers are not included in the theorem? Let's say n equal to 2, d equal to, let's say, 6, 8, 9. 8, 9 is they are not included here, but using these cycles, Aoki Shioda cycles, we can verify. So something else that even if that we are in the case of surfaces, and the case of surfaces we know the Hodge conjecture, but the question is different. We want to see that these algebraic cycles generate the Hodge lattice, and so it is stronger than Lefschetz 1 theorem. We can verify, let's say I call it the Hodge conjecture for n equal to 2. I mean not let's say we can verify the theorem. This one. For let's say n equal to 2, equal to 6, 8, 9. But something something that you will again will have difficulty. For example, surfaces, Fermat surfaces of degree 12, and so far there is no complete list of curves generating by Lefschetz 1 theorem. We know that such exists, but nobody has written the complete list of curves. Curves, because we are in the n equal to 2 case, generating H11, H2, X. Maybe I put it here, X, so we just withdraw. Yeah. And so you see that even in this case, Hodge conjecture is well known. If you want to do everything explicitly and construct, the things are not so easy. And actually 2 years ago, Aoki wrote me a correspondence. He told me that he's trying to find explicit expressions of missing algebraic curves to generate the Hodge lattice, in this case, Picard group or algebraic group. Okay. So at the end of the day, generalization of this kind of theorem for arbitrary Fermat is also a great challenge. Okay, let's go to the main topic of this talk. As I said, we want to replace the integral one. Maybe I'll tell also the story in this case. So, integral version. So let's put the whole result that I know. mainly it indicates about n equal to 2. So n equal to 2. Okay, maybe first I'll put the names. Shoot. Shioda. Shioda. So the same statement, just I will replace Q with Z. So, for which class the D less than 100, D equal to 6, N equal to 2, DU and 6 are coprime, N equal to, N equal to 2. Then there is the TRF. N equal to 2, and removing this condition, let's say, removing this condition. So this D less than 100 was mainly because their argument at some point they had to compute something by computer, and then just was able to go up to 100. So this. And this is 2015, and you see even that Lefschetz 1 theorem, we know it, the results are not are recent. And also, I will tell a result to, what these results are, the same statement, with Q replaced with Z. And in the middle, I will tell also a result to Dektiarov and Shimada. But now I am going to because it is much more related to what I am going to do. Yeah. 16. And in the middle, I will say what exactly they have done. Okay, so the point is that basically when you go to higher dimension,
what did they do? They wrote down explicit geometry?
No, exactly.
That's the content of the...
No, at the end of the day, all the statements is going to be linear cycles. And I will say, then I will tell our result, and then I compare, and in the middle, at the same time I am telling our result, I will tell also what they have done. Okay.
But only for existence, so lattice one will also cover the integral case.
No, all these results are integral case Q. Where this thing is doing. It is doing.
When this is Z, it's also part of that.
Yeah, of course. But the point is that we want to
explicit geometry.
We want to verify the linear cycle. Of course, by Lefschetz 1 theorem, the integral is true.
Yeah.
But it says that there is some algebraic curve. But it doesn't say that these linear cycles, the lines, are enough to produce the lattice. So as I said, this statement is stronger because it says that which list of algebraic cycles must generate a lattice. And that's why, for example, this is Lefschetz 1 theorem, basically, but there is this, the end is makes the things complicated, the lines. Okay.
Yeah, so Hossein, maybe I should just mention that having this overabundance of cycles far beyond what you need to generate, say, PIC, is extraordinarily useful for generation arguments. So when you're trying to play games with like the Hodge D conjecture, there's a student of Matt Kerr, Tokyo Sasaki, who just has reproved the Hodge D conjecture for a class of K3s, and he did it by explicitly finding the algebraic cycles. I mean, this is a in a field where proving the existence of a non-trivial class is a big theorem. Having the actual cycles that represent that class is a whole new game.
Maybe I just some history. In Griffith's article, when he proves a version of a Lefschetz 1 theorem, he starts saying, okay, we will construct such and such algebraic curves. But the concept of construction to Griffiths is at that time, it's really different from whatever we want to do here. For us, construction means that write down the equation explicitly. And so...
so for a host of applications in mathematics and physics, it's really important to have the actual...
Yeah, exactly. The actual cycle. Just so the idea is that Lefschetz one term is theoretical, but actual cycles is very difficult to write down.
Look at that.
As I said, I will tell you in the middle of
So, conjecture of linear. Chapter end?
Alright.
Oh, yeah, yeah. I communicated their former advisor. Robbie, yeah. Anyway, so, yeah.
Okay. So as I said, even so, if you construct a lot of algebraic cycles, verification of the Hodge conjecture, or say that integral Hodge conjecture is false, is doable, but it is as time consuming as proving new results. So this is this is my at least in this case I can say why this statement is true. But let's say let's try to
So let me say sort of a pessimist perspective on the old style approach, okay? So the way we go about proving most of these results involving the Hodge conjecture is in the old style approaches, you build filtrations and bifiltrations and formal linear algebraic structures. You then study their behavior under generation, and it's all very formal, very structurally valid. It is how you prove results like the Catani-Kaplan-Schmidt result. That's great. Okay? But at the end of the day, you have no control over the geometry. So, to my mind, this time that you spend, reproving old results, but explicitly, is by no means wasted. Because if you want to formulate new ideas, new theorems in the subject, you need new tools. And in particular, if you are a geometer like me, you want geometric tools, so you want to actually see the cycles. So anyway, so this is mostly me saying, I think Hossein's not wasting his time. I think this is great.
Okay. So let's I will put a lot of statements, and this statement update will give algorithm how to implement them and put in the computer and see this the result is okay or not. And of course, the disadvantage of this is that it will be working for particular degrees and n, because anyway, computer just understands particular d and n, and also you will get some result for limited amount of d and n. So let's do it. So first of all, the homology. So we have to know how is the homology. So I will book this affine chart x0 to equal to 1. So, and also there was this x0t plus blah, blah, blah. So since I'm doing complex algebraic geometry, just inserting -1 will not affect my variety. It will be isomorphic because we just multiply x0 with some root of unity. And then I will look this in a affine chart. At the end, my variety will be this one. Equal to 1 inside Cn plus 1, and for some historical reasons, I will put different exponents because it includes a lot of other nice, interesting varieties. Many examples also coming from let's say toric geometry. So let's say for us mi's are bigger than 2. For the rest of the talk, you can put m1 equal to m2, n plus 1 equal to d that you have. But what I'm saying that you can do all the things just for this class of varieties. Maybe one reason why I did this category because if you look Picard's book on multiple integral, there is a lot of examples which fit when you put this class of varieties. Okay, so we know perfectly well the topology of this guy, and this is mainly due to people in singularity theory. I don't want to pick just one name. Arnold, Milnor, found. And many really around 90s, 70s, there are a huge amount of people trying to understand, let's say, this equal to 0 singularity, and then they produced a great amount of results. But at the end of the day, if you look the results, and then you will get this fact that HNLZ is free. So the basic idea, I want to capture the topology of the compact X by looking at its affine part, because the computation will be done just in the affine part. So I have to know what is the topology of this guy. It's really generated by X. So maybe I have to say something like this. So maybe I first write and then. Okay. Okay. So.
What's
Yeah.
L? L?
Oh, okay. This is so the affine part. You the basic idea, you can construct explicit elements delta beta. They are so explicit that in the beginning of my let's say course in homology in topology, I give it as exercise because it is delta, and actually it is to save time I will not write it here, but this is a kind of exercise for 2 in the link is in the web page. So the point that this generator, they're have to say, you explicitly write down the simplices, and then you say that the simplices glue together, and at the end you have you get elements of the HNF. And writing formula will take time, but if you want to, as I said, you can write it. And at the end of the day, these delta betas, if you want some kind of history, they are parts of this union of delta betas as subsets of L. These are called Milnor bouquet. So there's a beautiful theory in singularity theory, and they are actually, let's say, spheres. Delta, let's say delta, they are spheres glued to each other in certain point, and so on. And so this means that at the end of the day, if you tell me that, well, give me a basis of the homology of this guy, it is, if you have done a course in homology, algebraic topology, then this you can do it as explicit as possible. And if you are interested in symplectic geometry, actually, let's say these delta betas, they can be represented as Lagrangians of a symplectic form coming from the Fubini study of the corresponding projective variety. So if even from this point of view, also you can do. So the moral of the story is that you can write down explicitly these spaces. So the problem, you say, okay, now I have a complete understanding of the homology. Explicitly, it's not just theoretical results saying that HNE is free generated and you don't know the generator. You write down explicitly the generator. Maybe I will do it in the case explicit generators in the Durand homology. I will write it. Maybe so. The next step is that the Durand homology and the Hodge filtration and the Hodge decomposition and so on. So even you know theoretically all this stuff, you have to be able to write down explicitly. And again, I will do in a fine part. So maybe let's say you can put more names. If this is 69, and I will have to put pre-score, or 72. And now, well, actually, I have to put the name multiple. But HN theorem. This guy also you can write down explicit basis of generators is if let's just take the usual C infinity theorem homology, because later I will use algebraic theorem homology, really generated by, in this case I can write the explicit omega beta, x beta, eta, eta is this alternative I minus 1, xi, then the xi. Check, again I will be back what it is. So beta, so the indices in this x betas are just monomials. x1 beta 1, xn plus 1 beta n plus 1. And they exactly the same range. In theory, we know that the homology is dual to homology. But and let's say, yeah. And this xi check means that the wedge product of all the xi removing the dxi. And so this means that we have also a basic, we have a concrete basis of the round homology. At the end of the day, we want to verify something for the compact Fermat variety. Not it's a fine part.
What was the x check again?
The wedge of all the xi,
Oh,
the xi removed. Okay, so let's define this x. So the xy my compact one, this primitive value or primitive value is 0. So this will be the image of so you have the restriction map. And actually, this contains the whole data of the drum, except one dimension contains the whole data of the drum homology of X. But you can write down, you can say that exactly this image is generated by what? At the end, you will just put image. Let me say is generated by. Let me try make. By omega beta. So maybe something I will introduce, let's say this I will be all these betas in Z n plus 1 with this condition. So this will be the set of my indices. Okay, so omega beta with A beta where? So I will define what is A beta. This is A plus 1. So Mi A equal to 1 n plus 1. So this is not supposed to be integer. And then beta. So when this guy is integer, these differential form that you see here, they have some residue at infinity. So we don't care about this differential form, and when it is not integer, they don't have residue at infinity. They give differential form in the compact variety. So we say that okay, we capture the homology of the compact one. When n is even, there is the kernel is one-dimensional, but this one dimension will not. You have to be careful about it, but at the end it will not.
Sorry, what was X, the ambient weighted projective space?
What
is X, the ambient weighted projective space?
No, the X was the Fermat variety. The picture is.
What is L?
So maybe I will make a picture, but you have your X Fermat variety. And then I kept this X01, and the rest I called it L.
Okay, great.
Zero. Zero equal to 0.
Oh, okay, so exactly. This is the x0 equal to 0, and the rest of is x0 equal to 1. Because we have the projective.
Yeah, it's relating with projective and affine.
Yeah. So the idea is that I can do computation, correctly integration, and sorry, that fine part. So I have to reduce everything to that fine part.
Okay. You mentioned you have these explicit generators in and singular cohomology represented by Lagrangian cycles. Are they special Lagrangian?
No, they are vanishing cycles if you know this.
Okay.
The symplectic Picard-Lefschetz theory. Then there are vanishing cycles, which at the end they become Lagrangians of the corresponding, let's say, corresponding symplectic structure. Okay, so we have also. So I will deal with this one. So we have also this the round homology, and the good point is that obviously we also know. We also know not exactly the Hodge decomposition, but because the Hodge decomposition is purely analytic. But Hodge filtration, we have, we know what it is here. And maybe I complete here, and FP, so maybe I remember, H and the round 0 is generated by. So it will be a subset there. So it will be omega beta with R beta less than n plus 1 minus p. And you have to put all these beta is in I. This guy is not integer, and so on. Okay. And what was, at some point I will define this algebraic theorem homology and the algebraic Hodge filtration. But if you are familiar with the analytic one, this is H n0 plus blah, blah, blah. I have, and then H, what was that? I always forget. P, and let's see. When you put P equal to 0, it will be the whole, yeah. And well, I have to say that if there is a 0 here, this will affect just one dimension, the middle piece, which is the polarization and so on. But let's just ignore this one. Okay, so I know how I have, let's say, complete understanding of homology that I can implement this delta beta in the computer, the differential forms. But before this one, what I have to do, we need integration. Last time I wrote the definition of Hodge cycle by integration, that's just intersection of lattices. So we need intersection also. Maybe the first time this integration, it is very simple integration done in the literature is by Devine and 82. Of course, not in this language, but basically the things is there. So you have omega beta prime, delta beta. You can integrate it and you have explicit number. Maybe I write this one. N plus 1, beta plus 1, N1, beta N plus 1. Maybe, okay, it's a bit beta, this will be, okay, here the beta 9. So beta prime will be the index of the differential form. N plus 1 plus 1, n plus 1. And then this is the beta function, I will write it, and there will be up here the algebraic number. Beta I plus 1, beta prime I plus 1. This is just really a calculus integration. And minus beta n I beta I prime plus 1. If I have made a mistake of my indices and so on, then just in my theory book, everything is there, and you can trust it because, as I said, the things are implemented in computer and checked, rechecked to be sure that everything is working. So what is the results of integration? There is some nonsense or the rational number. There is this beta function, beta a1, a2, blah, blah, blah. It's just this gamma a1, gamma a2, blah, 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 and then gamma a1 plus a2. So yeah, the gamma is the gamma function. And for our story of the, let's say, just define the Hodge cycle, this will not affect. And the rest is an algebraic number. Zeta d is the d root of u. Zeta and I is Okay.
Okay, could I ask really briefly, what's the idea of this Griffiths results? Like you're using meromorphic differentials to represent these mixed holomorphic, anti-holomorphic differentials?
Yeah, this is about they are meromorphic at infinity.
Okay.
But if you say you write the long exact sequence of the inclusion of that fine part in the compact one, you will see that they induce something in the T-infinity differential, T-infinity homology. But as I said in my first lecture, I said there is this algebraic Derang homology to the protendic that then justifies that all the features of the algebraic classical Derang homology you can capture by algebraic.
Okay, great. So just the explicit like mixed holomorphic, anti-holomorphic differential you get is just like applying DD bar a bunch or something?
Exactly. I will not use the D-bar stuff. I will try to do purely in the topological plus algebraic context. I will not use the D-bar stuff.
That's fine, but just like that's what the map is. Okay, yeah, sure.
Okay, maybe I write down the definition of
No,
that side.
I don't want the definition. That's all right. I mean, unless you were going to do the definition.
God damn it.
So, okay. So once you have all this data, then you can implement and compute by computer the Hodge cycles. So let me again put the definition of Hodge cycle. Delta in. So I will capture Hodge cycle just in the affine part, but as I said, the difference is just one dimension. That's x, z, with suffering, and L is called Hodge cycle. If so, delta equal to 0. And for definition of a Hodge cycle, you need just a piece of the Hodge filtration. And what is this piece? Maybe I write down explicitly in A beta less than 2. A beta is the package integer. And that then beta is in Si. So this will correspond to the Hodge cycle that you see the literature up to some primitive part. That for the moment I don't care about it. So let me see. Okay, so I have a basis of vanishing cycles. I have a basis of Derang homology. I integrate them over these. I get a huge matrix. This huge matrix will contain this algebraic number. You will see that this transcendental number will not bother me in the definition of Hodge cycle because this is equal to 0. The transcendental number just depends on, let's say here, just depends on differential form. So it can go out and it can disappear because you have the equality. But they have some contribution to Hodge cycle that later I will tell. So at the end of the day, the moral of the story is that you implement everything, you can write down a basis of the lattice of Hodge cycles, and this everything is, as I said, implemented. Maybe I get just, and in particular, you can compute the rank of Hodge lattices and so on, but it's not just the rank, as I said, even you get explicit basis. Maybe let's say right there, 4, 3, 4, 4, 4, 5, and reaching to Calabi-Yau fourfold Fermat, 4, 6. So in this case, H22. This is the full H22 is 21, 142, 581, 1752. Let's say rank of lattice. So in this is again 21, 142, 401, the same number. So the first thing that you can do, you can compute the rank, which is again, in this case, I don't know if somebody in the literature have computed already. I think but you can compute these ranks when the rank of the Hodge lattice becomes as the maximum one, which is the H22. There is this Beauville's row maximal concept, and you can also generalize it in the context of a higher dimension. For example, this is row maximal, Fermat fourfold is row maximal, but the quintic fourfold is not row maximal. So the rank of that is 401, 581. So this one, it doesn't matter. But as I said, the idea is that really to understand the lattice structure concretely. And the lattice structure contains intersection pairing. And so the way that I am going to this verification of integral Hodge conjecture by comparing the two Z modules as lattice. So I need formulas for the intersection pairing. And fortunately, this I have to maybe, let's say, also put, well, I put my name because you don't really, you have many things, prove that things in Fam's article, but at the end, one has to a little bit modify the argument and to get this one. So the next two results are that you can compute also the intersection pairing and implement in the computer. So I will do this one. So when you have, these are n-dimensional cycles in two n-dimensional variety, so they have, these are integers, so for two cycles, so the basic idea, so you have one delta beta, the other delta beta, and you want to compute exactly the intersection. So the result is this one, minus, well, this is depending on n is anti-commutative. The self-intersection is basically the self-intersection of the vanishing cycles. So delta beta is minus 1 to the n plus 1, 2, 1 plus minus 1 to the n. And then there is this, the other one, delta beta line is minus 1. Minus 1, n plus 1, 2, minus 1, k equal to 1 until n plus 1, beta I prime minus beta I. This is for those beta and beta lines that beta I is less than beta prime I, less than beta I plus 1, is greater than beta I. And beta is not the same as beta line. And the rest is just the rest. Yeah, the rest is 0 up to, if of course you don't compute or you don't switch the place of beta line and so on. So at the end of the day, we can write down that this huge matrix of the intersection pairing between beta line. So, okay. So the integral Hodge conjecture in this case, it was, I want to check that two lattices are the same. One lattice is inside another one. What I will show that the discriminant of the both lattice is the same. This will be, the idea is to compute the discriminant of the both lattice. So now I need what? I need the intersection of the algebraic cycles. So let's say adjunction formula. It will give me the other one, Pn check. So let's take this Pn2 check, one of these many linear cycles inside Fermat. So you will see that they can intersect in many different ways. The topological intersection might be another Pm. And so this M can vary from -1 to 0 until 2. So this is the topological intersection, but I will have also, no, let's say this is a set theoretic intersection, but I want to compute the topological intersection, which is just a number, not a set. Then the adjoint conjunction formula then will give me this nice formula. So the intersection of P, these two guys will be a number, an integer, which this number is divisible by D, so this is the formula for the topological intersection. Okay, so now we have more ingredients to implement in the computer, and you see that the matrices that you will get, they are huge, because the first the capital N number for bigger D, bigger N is huge, and also how many of delta betas you have? This cardinality of this I in it is just M1 minus 1 and plus 1 minus 1, which in the case, in our case, all m is equal to 1 is d minus 1 to the n plus 1. Which when your d and en grows, they are, at the end, the matrices are huge. Okay, so so then you start also to implement all these data in the computer. At the end of the this to be sure that all the formula that you have written, everything was okay, they are working in practice. Sometimes you prove something, there is some minus signs from them, and in practice it doesn't work, but these formulas work in practice also. So then maybe I will a little bit. Okay. So at the end of the one writes the basis of two objects. First of all, the Z module generated by the topological class of these linear cycles in H and XZ. One bit also about this polarization stuff, but okay. And the module, and the second D module, this is the first one, and also the second Z, let's say the D module, that lattice, let's just use the lattice generated by K. And of course, the second, the other one also, the Z, the lattice of Hodge cycles. And maybe I give here a name. Let's do again use the traditional this classical notation. So this lattice I denoted that's the usual one. But as I said, we will work on homology. And the other one, let's say this other one, let's denote it by let's say Hodge. Okay. Okay, then let's do this one. Okay. I have to produce some. So, another name is the LPNs. So at the end we know that this LPN2 is inside H and 2 and 2 it's HXM, because any algebraic cycle is a Hodge cycle. And so a basis, let's say, so you compute the basis, let's say, call them in both cases, let's call it gamma I. So actually we have two set of bases of B. And then what you compute, this huge matrix, the intersection matrix, which is B times B. Both intersection metrics, the intersection for both lattices, because in both sides you have closed formula and so on. And okay, so in order to prove that the both lattices are the same, you have to say that they have the discriminant. This means that they have the same determinant. And maybe I write just two examples of the determinant or discriminant. N equals ND for 5. Here you will get the determinant of this gamma I G is equal to 1 plus. I will write in this way and I will explain that there are some meaningful numbers that here. 1 times 166, which is 1, but in a minute I will explain why I write in this way. 5, 1, 7, 5, 7, 4, 25, 4, and maybe I just write, in this case, it is minus 1. I did not even write the whole, blah, 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 but at the end there is some 6. And at some point I was trying to understand how for the second number is big. Apparently it is bigger than, let's say, the number of particles in the universe, but they are very, very huge numbers. Okay, so the strategy, at least for the verification of the integral Hodge conjecture, you just compute the determinant, and then the determinant will be this one. So if you just give the computer calculate the determinant, it will not give this huge number. So the point is that you are not supposed to multiply the numbers. That's why I have written this. So if you do the Gaussian algorithm, you have to just keep the number that appear in the diagram. So this is why it is written in this way. And if you are working over integers, Gaussian algorithm is not good because it's over rational number. What you will use is actually Smith's normal form. Which is a finer version of the Gaussian algorithm for matrices just over integers. So at the end, when you compute so maybe let's write it. So if this is A, at the end of the day, this Smith's normal form will write your matrix as A, T, S, S. This will be diagonal, and then let's say determinant of U is plus minus 1. Everything will be over integers. This will be T equals plus minus 1 also, and this is diagonal A1 until AB. So at the end, this list that you see is just this A1, A2 together, the repetition. So this means that 160 times, 66 times the 1 is repeated, and so on. So in this case, okay, maybe I have to say something. In this case, you will get the verification of the integral Hodge conjecture. But in this case, in the second case, I have to modify a little bit my discussion. In this case, one has to replace HN2, HN2, HNXZ with something which will be, I will call it, put Pn2 here. So the point is that for definition of Hodge cycles, you know you have a bunch of integrals equal to 0. But even some integrals from the middle piece of the ramp homology are automatically zero on some cycles like P in, similar to P in our two cycles. So at the end you have something which are conjecturally generated by linear cycles. But, and it is given by vanishing integrals, and you don't see. So you have to do all these computations, and actually this number will be the discriminant of this one, and of course the discriminant of the lattice generated by linear cycles. And then, well, maybe I have to say that in this case you need another cycle. If you want to do further, you will need these Aoki-Shioda cycles to try to prove the full integral conjecture here. But for that one, some formulas are missing. Maybe, okay, let me say a little bit further. So if I didn't make definition of this one, you must just take this case and a few other cases which you verify the full integral Hodge conjecture using linear cycles.
How generally do you expect the integral Hodge conjecture for Fermat hypersurfaces or weighted hypersurfaces?
Well, at the beginning I was expecting, for example, something this might be also wrong. But in this, for example, quintic fourfolds Fermat, the integral Hodge conjecture is true by the computation. And now I don't have any idea of. Well, I was hoping that to get new example, or at least new possible example for integral Hodge conjecture just by Fermat. But so far it is just checking that it is true. But I don't have any idea if how far one can.
This computation doesn't work. It doesn't say that the integral conjecture is not.
Yeah, exactly. The point that.
It's just that the
For the full Hodge conjecture, in this integral Hodge conjecture, in this case, you have to produce similar formula for algebraic cycle, but I call them Aoki-Shioda. That I didn't write them. But the explicit expression of the algebraic cycle I have reproduced in book. It comes from Aoki-Shioda article. But for example, the intersection of the Aoki-Shioda cycle with other linear cycle, this is not written, then you have to go do this exercise in algebraic geometry, take that adjunction formula, and do everything.
Okay, sorry. Just to understand what you said, originally you said you wanted new counterexamples to integral Hodge from Fermat.
At the beginning I was expecting, but it's not. Apparently, integral Hodge conjecture is going to be kind of true for Fermat.
Okay.
But even if your computation gives negative result, it just tells you.
Yeah, exactly. It will not be a counterexample because you might be able to produce new algebraic cycles. Yeah, this is that. So at least for me to do this job is that I want to understand as much as possible the Fermat, and then to try to do my Hodge Loci stuff looking from Fermat. But of course you can push forward all this idea to see how far you can go. But I have not done this one. Okay, so maybe maybe this Shimada is the TRF. So the Shimada declared article appears, let's say, a year and a half before us. And then the point is that they are also able to verify this kind of statement, at least this one. And their method is basically based on the computation of the intersection of the vanishing cycle, this delta beta, with this. So you take the algebraic object, you get the topological object, and you get a very nice formula. And using this one, you can also try to verify. But something which in their method doesn't appear, for example, the discriminant, and I want to make some statement using this discriminant, it contains some non-trivial data. I think they might be related to a talk homology of the Fermat, but for the moment they are obtained just from purely topological study. But maybe, for example, I say some interpretation of this 166. And Okay, maybe I have to say that this whatever I told this is from this Hodge theory book, chapter 15 and 16, and also my joint work with Villaflor, and this is. But there is just one article in the archive with these 3 persons. So maybe I said that at least this kind of computation is not reproduced in their context. So for example, what you can claim, that is, again, I will tell a sample example, the lattice cycles. Or let's take just one example for 5. Of course, when you do mod 5, the discriminant is 0. Mod 5. The discriminant is 0 because all these factors are 0. And you can ask what is the largest sublattice of this, our FP, of this non-zero discriminant. The latter mod 5 is as discriminant equals to 0. Of course, this you see from just the number, and it's so in this case, mod 5 you get the FP vector space, and its largest sublattice of this grid. So its largest lattice, which is has non-zero discriminant, will be just this 166. So I have made mod 5. So now my vector space is mod 5. The rank. So when you make mod 5, you have some, let's say, it is ambiguous. When I make a mod 5, I have some lattice which is discriminant 0. So I quotient it by all elements which their intersection with any else is 0. I will get smaller, and its rank will be 166. And then something which can be observed that these are really invariants of the lattice. We get them from the Smith normal form, but how you can justify this invariance, I don't know. As I said, maybe this has to do with the homology. I'm not sure. And yeah, well, this is what I wanted to say today. So as I said, in the middle of the order talks, I will also, if I need something from the Fermat, I will repeat it. So the idea is, as I said, we want to a little bit perturb Fermat to some hypersurface and to analyze the Hodge locus around Fermat. Okay.
So for Fermat surface, for example, take a quintic Fermat surface in characteristics, say, so let's say K3, okay, the quintic K3 Fermat. Take characteristic 3 orders, 3, say. Then it can be shown that all cohomology classes are algebraic, actually.
Quintic K.
No, quintic 3.
No.
Degree 4.
K3. Okay.
K3.
Degree
like
4.
In characteristic
So this is the row maximal, yeah.
Yeah, the Shioda. No, actually, so usually it's the largest possible is 20, right? But actually in character 3, it's 22. There are 22 algebraic cycles on this K3. So I wonder.
22 algebraic cycles.
Yeah, because over complex number we have Hodge decomposition. So there's a constraint on these 2 cannot be algebraic cycles. But over like in characters 3 is.
Okay, you are doing a characteristic.
Yeah, so Shioda has a paper about this.
Okay.
Actually, he proved that in character 3.
I'm not really
Yeah.
expert in for my characteristic 0 for the moment and topological.
Yeah, but as you said, it's.
Maybe we can discuss further.
Yeah.
But I'm sure that these numbers must have something to do with, for example, how bad is your Fermat characteristic in 5?
Yeah, that's why. Yeah, it's of course it's singular in characteristic 5. Like it raised to the 5th power, and it's just one single equation. It's a hyperplane.
Yeah. But if you give me the interpretation of this number, I would be very happy. Okay, so something next week, Wednesday is holiday. I wanted to make some extra talk Thursday. Wednesday is holiday. No, somebody
Thursday
told.
also fun.
Thursday is a major holiday. Wednesday, you can still public and do anything.
Okay, Wednesday is the usual day.
Yeah, Thursday is a Thanksgiving.
Okay. So then we will have the usual. I don't know.
Wednesday is artificial holiday.
Okay. Okay, so